All right, hello everybody. Welcome to week 9 of the spring semester. It's kind of hard to believe, but we are now officially halfway through the semester. Normally, on a normal year, this time, right now, we would be on spring break, but of course, that's not what was in the cards this year. So we have 16 straight weeks of school, but we'll get through it. How's everyone doing? Good, bad, neutral? It's been an all right week for me too. It's been a great day for storm chasers down in Dixie Alley. Has anyone been keeping track of what's the severe weather that's been going on down there? Um, Personally, I haven't been able to keep track of it much today. I've been really busy. Has anyone actually been keeping track of any specific events that have been going on down there? Let me see here. I can go ahead and share my screen. I can talk about it a little bit. Where's it? Yeah, here we go. So if we look at the, let's see, this is the convective outlook here for today. You can see this big patch of pink right here, right in the heart of Mississippi and Alabama, with the high risk of severe storms. This is rare. I'm not exactly sure how rare high risk zones are for this, but it is very rare to have for the National Weather Service to be so certain of widespread severe storms and tornadoes like they are today. And so this is actually quite a historic day, especially for a lot of people in the National Weather Service who haven't worked on a day with such high severe weather potential before. Um, some storms have already spat out tornadoes today. We can look at the preliminary storm reports here for the 17th. So far, we've had 18 tornado reports. Obviously, that number is still subject to change once they filter the data and make sure that they're not double reporting or anything like that. But even so, we've had over a dozen tornadoes today so far, and it's far from over. I did a little bit of reading up on it this morning. There were actually expected to be 2 rounds of storms today. So around early to mid-afternoon, there was going to be a large scattering of isolated cells and supercells that would be possibly tornadic. And so that's what's caused all these storms and tornadoes right here are those early day storms. And then additionally, later this evening, there's going to be more storms associated with the cold front that moves through. It's going to be a set of linear storms with supercells embedded within that. You can actually see this right here if we look at the current radar. You can start to see that linear structure developing already down here in the south that's associated with that cold front. This is actually going to cause a big problem, not only because it's rapidly approaching nighttime in that region, but also for with those supercells to be embedded within that linear storm structure, it's going to be really hard to see those tornadoes. They're going to be almost certainly be rain wrapped, and that combined with poor visibility conditions down in that region to begin with, and the nighttime, it's going to be really hard to see those tornadoes. And so I do pray that people are staying safe, especially the storm chasers down there, making sure they're not putting themselves in any potentially risky situations. It's not just today either. As we go on to tomorrow, there's plenty of severe storm risk out east, specifically in South Carolina, Georgia, and North Carolina. They're in that moderate zone there. So again, lots of severe storm potential in these next couple of days. So yeah, I'd thoroughly recommend keeping track of these storms throughout tonight and into tomorrow, trying to see what comes of them. Hopefully there won't be too many deaths or anything associated with that. But yeah, very exciting day for weather. We can move on to club business now. As I'm sure you guys are aware, we now have t-shirts and we are now officially ready to order them. Here's the design right here on a shirt, so you can actually get a good picture of that. These shirts are going to be $20 each, plus $1 for each X you add onto the size. So for example, if you get an extra large, it's going to be 21. I don't like doing that, but Custom Ink requires it. And so obviously we got to charge more as well just to make up that cost. But yep, $20 a shirt. You can email either me personally or the Severe Weather Club email to place your order, and then we'll accept payments via the Severe Weather Club PayPal. Or if you have a class with me or something, you can arrange time with me, and I can just take your order by cash. That would be fine too. But yeah, exciting. We're actually going to get a shirt this semester. We had our last shirt canceled in the spring semester of last semester, and so then last spring. Then we did the meteorology shirts last fall. So it's good to have another club T-shirt. Other just general announcements. We've announced this the past couple of meetings now, but don't forget DBN is having storm spotter classes. There's one tomorrow that I'm going to, and they're having them all throughout March and into early April. So be sure to go to one. I do recommend it. And again, Dr. Finch offering extra credit, so you got that added incentive as well. Additionally, for the Severe Storms Conference, if you're going to that, they've finally released the actual lineup by times. You can find that on their Twitter, Central Iowa NWA. I'll enlarge this image for you. But basically, yeah, they actually have all the speakers in order and what times they're going to be doing it. It's actually really nice. A lot of the conferences that I've been to in the past, they have a lot of overlapping speakers. And so what happens is, like, I'll have 3 talks that I really want to go to, and they're all scheduled at the same time, so I have to miss them. But there's only 1 talk per time block, so you can watch all the conferences or all the talks if you wanted to. Additionally, if you only wanted to watch, like, for example, Dr. Jeff Trapp's speech and then maybe Nick Stewart's in the afternoon, you don't have to attend all these to get your money's worth. But yeah, if you are going to do that, then that's right there for you. If you're just considering going, I do recommend going. It's only $10, and some of these speakers are really awesome. Does anyone have any other comments or concerns that you want to talk about before I start my presentation for this week?
Yeah, about that. Do you because I registered for it as well, but as far as like payment goes, do you know how they usually do payment? Because I know it's a PayPal, but like I don't know where to send it because the email address for them doesn't work.
Really? Okay. I wasn't actually aware of that. I haven't registered yet. I've been waiting to get the money for it. I don't actually know. That would probably be a question for Anthony. I know he's registered. I can go ahead and shoot him a text, and then I'll get back to you as soon as he responds to me. Yeah, it's strange that they haven't established a payment place yet. But yeah, I'll get back to you as soon as I can on that.
All right, thank you.
Yeah, no problem with that. Anything else? All right, then with that, I guess I can start my presentation. I'll give my spiel, my usual spiel as always. If you guys have any questions, feel free to interrupt me. I can't see you guys on my screen. So I'm more than happy to answer any questions that you guys have. But basically, this presentation idea I was actually looking into the idea that you suggested, Jax, about volcanic causes of weather as well as stuff regarding nuclear radiation. And then I got kind of in a rabbit hole of things that had really nothing to do with that topic, but I thought were interesting. And so I actually decided to delay that topic idea for maybe another future presentation. And instead, I just kind of wanted to focus on unique ways to create interesting weather. Something to keep in mind with this presentation is that not only do I want to look at interesting weather, obviously we're going to look at some cool weather-looking things, but more so, I also wanted to focus on, oh, excuse me, specific, unique ways that weather can be created. As meteorology students, we obviously study the traditional methods of, weather creation, fronts, mid-latitude cyclones, upper level divergence. You can group short waves into that mix. And there's good reason that we study those things, is they are the primary drivers of like 99% of our weather. And so it's really important that we understand the mechanisms that drive weather traditionally, especially the mid-latitudes. But, sometimes it is really interesting to just look at some either uncommon or just really unusual sources that weather can be created. Not only that creates unique, interesting weather, but also just, exciting ways to create mundane weather. And so before we begin, I guess I want to apologize if you've heard of most of these things. I just learned them through my courses at WIU. But I hope there's at least a couple of these that you haven't heard of, or at least you're like, whoa, that's kind of interesting. But yeah, to create weather, all you really need is rising air and moisture. And so when you think about rising air, obviously you think about fronts or that kind of thing. But what about just a big old mountain? If there's a mountain in the way of moving air, obviously that air isn't going to go anywhere but up that mountain. So obviously we all know about lifting air over a mountain. We study that quite a bit in our meteorology classes. That process is called orographic lifting, and it's responsible for a number of weather and climatic effects that we study quite a bit. For example, the rain shadow effect. As we know, as air moves over a mountain, it's going to squeeze out its moisture in the form of clouds and thunderstorms on the windward side. And so on the leeward side of the mountain, all that air comes back down really hot and dry as a result of the fact that all that latent heat from the moisture has been released into that air and the moisture is now gone. And so that's why, for example, the desert southwest of America is where it is. It's in between those mountain ranges, which means that it's going to be very hot and very dry. This effect is also responsible for something called the Foehn wind. If you're in Dr. Choi's 327 class, or if you've taken that before, you know what the Foehn wind is. But basically, it's when in a mountainous region, a large billowing mass of air billows down the mountain and gains a lot of heat really, really fast, and then it spills into a region. And so that kind of phenomenon can raise temperatures like 30 or 40 degrees within the span of an hour. And so it's really quite remarkable in some like mountain valleys, if there are towns there, they'll experience some very massive heat spikes sometimes as a result of Foehn winds. Additionally, orographic lifting is responsible for this rare type of cloud event called lenticular clouds. I'm sure you guys have seen pictures of these before, but I think they're quite fascinating. The way they're created is fairly complicated. The layman's answer is when really stable air is forced to go up a mountain, obviously stable air does not want to rise. And so when it gets over that mountain, it does squeeze out some of its moisture. And so that's why we have the cloud in the first place. But once that stable air reaches the mountaintop, it says, well, I'm not going to rise anymore. And so that's why the top of the cloud is coincident with the top of the mountain. It's a bit more complicated than that. It has to do with standing waves as a result of wind flowing over the mountain. And so that's why sometimes you'll see pictures of multiple lenticular clouds right on top of each other. That's a result of atmospheric, like short, local scale atmospheric waves causing those clouds. But yeah, lenticular clouds, very cool, at least in my opinion. I really like them. Another way we can create lifting is via surface convergence. Now, I'm not trying to say lake effect snow is a unique cause of weather. We all know what lake effect snow is. Basically, it's when very cold air is evected over a warm lake water. The temperature gradients results in a lot of moisture being added to the air. And then when there's surface convergence at the boundary between the lake and the land, all that air rises up and creates snow. We all know about lake effect snow. Occurs predominantly in the Great Lakes and Lake Superior. We've all heard of that. But have you guys ever heard of nuclear cooling pond effect snow? It's a pretty wicked sounding name, but it's actually very, very similar to the same process that creates lake effect snow. It's when cold air advection happens over a cooling pond at a nuclear power plant. Now, if you think about it, cooling pond at a power plant, there's nuclear fuel in there, and so that radioactivity heats the water quite a bit. And so there's a very large temperature gradient between that pond and the cold air advecting above it. So what that means is a ton of moisture is going to be advected into that air, and then it's, of course, gets swept along with the wind to places downstream. And so it causes narrow bands of snow downwind of power plants. These bands of snow are typically very narrow, but they can dump a lot of snow, like up to 3 to 5 inches in like an hour, depending on the conditions. This is a satellite image, this is a radar image rather, taken in Pennsylvania, I believe. So here's obviously the location of the power plant and the snow associated with those cooling ponds. This also happens in Illinois. Here is the LaSalle County nuclear power station in LaSalle County, obviously. And you can see right here, this plume of white is actually nuclear cooling pond effect snow as a result of that power plant. And so I think that's just a pretty interesting way to create weather, and specifically snow. Next, I kind of want to transition into how we create thunderstorms. If you were in hazards today, you know where I'm going with this. Dr. Finch kind of beat me to the punch here, but if you think about what kind of storm conditions you would want to create, or what kind of conditions in the atmosphere you'd want to create a storm, what you would want is really hot, unstable air at the ground, moisture aloft, and then, of course, all of that warm, moist air rising into the atmosphere. And so when you think, okay, well, what kind of atmosphere or what kind of conditions would create that kind of atmosphere? Well, you've actually just described a wildfire, basically. If you think about it, wildfires, of course, generate tons of heat by burning the vegetation around them, which warms the air, which then causes it to rise. This rising air creates an updraft and an inflow, just like a normal thunderstorm does. So what you do is when you lift that air into an environment with some water, you can create thunderstorms based on wildfires. The result is called a pyrocumulonimbus cloud, and it is literally just a thunderstorm fueled by a wildfire. Now you might think, okay, well, won't the rain put it out? The answer to that question is usually no. Oftentimes, it's just so warm in the ground where that fire is that the water evaporates well before it reaches the ground. Now that causes two things. One, the rain doesn't reach the ground, and so the fire doesn't go out. And two, that results in downbursts. If you remember my presentation a few weeks ago where we talked about downbursts associated with a severe weather outbreak, obviously, downbursts are just really fast currents of sinking air that then spread out. Think about it, downbursts create just massive wind currents at the ground, spreading the fires. Additionally, when lightning strikes associated with these storms from the cloud to the ground, they can create wildfires where there weren't any before because there's no rain to put them out. Of course, because there's no water falling into the wildfire, just like with supercell thunderstorms, for example, there's no cutting off of that updraft. And so these storms can literally last for days and days and days. If you see some of the pictures on the right here, you can see that they're kind of wicked looking. There's that smoke plume underneath the cumulonimbus cloud. Here's another picture from above. You can see that fire down there. And then, of course, the storm clouds right there. Here's a satellite image of one. So you can see that, I'm not exactly sure what the scale of this image is. It's at least dozens of kilometers across this. You can see that here are the fires, and then you can see this pyrocumulonimbus cloud is just stretching for miles beyond where the fire is. And so you can imagine if there's lightning that strikes anywhere from here to the ground down here, there's probably not fires down there, but it can cause fires because there's no rain. It's going to cause even more fires. And so that's one of the big dangers associated with wildfires is the creation of thunderstorms, which fuels more wildfires. On a similar vein, we can talk about volcanic lightning. This is where that sort of sidetrack in my research kind of came in. But yeah, if you think about in thunderstorms, the mechanisms that charge lightning within the cloud, it's usually associated with exchanges of charges between ice and water droplets moving through the storm. Basically, ice and water droplets will bump into each other and exchange charges. This is the same process that happens within a volcanic eruption. Basically, it's a combination of ice and ash exchanging charges through friction. It's the exact same process that you create static electricity with your socks in the carpet. It's called the triboelectric effect if you ever take E&M. But yeah, so that's the process that creates lightning in both thunderstorms and volcanic eruptions. So you can see on this picture on the right here, really fascinating lightning storms are often associated with erupting volcanoes. Additionally, because there's so many more particles in the air, there's generally a lot more lightning and a lot brighter lightning and a lot more intense lightning associated with these volcanic eruptions. And so you can get some pretty spectacular pictures. Something else that you might not associate with volcanic eruptions is a lot of water. But of course, there's a lot of water content trapped in the earth. And so when eruptions happen, it launches all that water into the sky. And so what happens is you'll have this water vapor that goes into the sky and then condenses, and then it falls back down in the form of ashy hailstones. And so sometimes downwind of volcanic eruptions, you will actually have hailstorms, which is definitely not something you want to have happen when your community is currently experiencing volcanic eruption. This is an example of a volcanic hailstone. This is about 3 or 4 inches across, so these can be very, very damaging. Also, this is different from something you'll hear here called lapilli, which is like basically glass that falls out of the sky. It's very similar to hailstones. This is actually ice and ash mixed together. So now I kind of want to transition away from that and focus a bit on tropical storms. And the first one I want to talk about is a phenomenon called metacanes, which are like hurricanes, but a bit smaller. They have a more boring name. They're called Mediterranean tropical-like cyclones. But as the name suggests, they are literally tropical cyclones that develop in the Mediterranean Sea. Something that you might think of when you think of tropical cyclones in the Mediterranean Sea is, well, that doesn't really make sense. The Mediterranean is at 37 degrees north, whereas typically you'll expect hurricanes to develop around 10 to 15 degrees latitude. And so for tropical cyclones to develop here is pretty unusual. They often develop in the region of the sea between Italy and Greece, although they can happen in multiple places around the Mediterranean. These things are typically a lot smaller than hurricanes, anywhere between 70 to 200 kilometers across. For reference, the average hurricane is around 500 kilometers across, with the largest ones ever recorded being over 2,000 kilometers across. So these things are really small. Additionally, they can have max sustained wind speeds between 29 to 110 miles per hour. So at their most powerful, they can be around as powerful as a Category 1 hurricane. At their least powerful, 29 miles per hour is really slow, especially for a warm core low like you would expect a hurricane to be. So pretty surprising how slow these things can be. Despite their name, tropical-like cyclones, there's actually really no difference between the dynamics of a Mediterranean tropical low and a normal tropical low. They have the same characteristics. It's a non-tilted warm core low in an atmosphere of minimal shear. And it's obviously rotating cyclonically. The real difference between them is how they form. As we know, in the mid-latitudes, low pressures are not straight up vertical, but are actually tilted, which is to say that the surface low pressure is at a different location than the upper level low pressure. So what happens is when the low pressure system reaches the occluded stage, the surface low pressure becomes disconnected from the fronts, and it actually becomes coincident with the upper level low above it. So what usually happens is that when it's disconnected from those fronts, there's no temperature gradient to fuel it, and it just kind of spins until it dies. But sometimes when the conditions are right within the Mediterranean, when an occluded low forms like that, rather than weakening, it actually strengthens due to, for example, really warm air. And so what it'll do is it'll actually strengthen and gather storms and take on tropical characteristics. Then it'll spin up to look like a hurricane and then hits one of the Mediterranean bordering countries. These things are pretty rare. The Mediterranean just doesn't really have tropical cyclone development conditions. Obviously, it's in the mid-latitudes, and that in combination with just unfavorable geography means it usually doesn't happen. But sometimes it does. You can expect between 1 and 2 metacanes a year. This is an example of one on the right. I think this satellite image here, this is the northern coast of Africa. This is the country of Libya. So you can see just how tiny this thing is. Like, this thing is probably no more than 100 miles across, whereas hurricanes are usually typically 300 miles across. But like, it has a well-developed eye. It has spiral rain bands. It really is just a miniature hurricane, and I think that's really kind of cool that you can find tropical cyclones in the Mediterranean Sea where you would definitely not expect to find them. Speaking of weird tropical storms, you might have seen a graphic like this before that kind of is a graphic of all the known tropical storms that have ever been recorded on Earth. And so from this graphic, you can kind of see the hot spots of cyclone developments. Obviously, the Northern Atlantic, Eastern Pacific, Western Pacific has a lot of hurricanes as well as the Indian Ocean and Australia. We all know those. But you might look at this map and you might look at something down there and you might wonder, well, wait, what is that? Well, if you've been in dynamic meteorology, you've heard Dr. Fitch talk about this. That was Hurricane Katarina. On March 25th, 2004, a hurricane-like storm hit the southeast coast of Brazil. I say hurricane-like for a specific reason, is that there's actually a pretty sizable debate, even today, as to whether or not this storm was actually a hurricane. We'll get into that a bit later. The storm hit as a Category 1. Something to keep in mind is that the Southern Atlantic is just not really conducive environment for tropical cyclones. There's typically a lot of wind shear, which is really antithetical to the development of tropical cyclones, which have to be vertically stacked. Additionally, low sea surface temperatures mean that even if there is a cyclone or a tropical cyclone that develops, it usually can't be sustained just due to low sea surface temperatures. But in late March 2004, anomalous conditions happened that did just happen to be able to support cyclonic development. And so what we see is that this hurricane developed very uncharacteristically of a hurricane. They actually developed very similar to how metacanes do that we discussed earlier. Basically, a non-tropical cyclone, a mid-latitude cyclone, basically, wandered into this environment of unusually conducive tropical cyclone development. And this low pressure system basically was able to chill out here in the Southern Atlantic, gather storms, turn north, and then head back west, spinning up, acquiring tropical characteristics, and then hitting the southeast coast of Brazil. To date, this is the only tropical cyclone with hurricane force winds ever to hit the country of Brazil, and many say that it's probably a once in a lifetime event, just simply due to how rare hurricanes are in this region of the world. Now the question here is, well, was it actually a hurricane? If you ask the Brazilian government, they'll say no, and they have basically vested interest in saying that. You know, the Brazilian government likes to say that Brazil is not a place where you will get hurricanes. You know, it's the safest place to be, so you won't ruin your vacation, all that stuff. And there's a good reason. There's a good argument for that too. You know, hurricanes don't develop in this way. They don't develop via the death of an extratropical cyclone that then turns into a tropical cyclone. That just doesn't happen. On the other hand, I mean, just look at it. It looks like a hurricane. It's a warm core low that's rotating cyclonically. It's vertically stacked, and it has hurricane force winds. And I'm not trying to say I'm an expert on this, but I mean, if it looks like a hurricane, acts like a hurricane, quacks like a hurricane, it's probably a hurricane. And so that's why most meteorologists say that, yes, this actually was a hurricane event, even though some, especially the Brazilian and South American meteorologists, say no, that it was not. So we're nearing the end of the presentation, and I decided that in addition to unique causes of weather, I just kind of want to look at some cool clouds. Can't have an interesting weather presentation without looking at some cool clouds. We've obviously looked at lenticular clouds already in this presentation. The first one that I want to look at is the roll cloud, also called the Voltus cloud. These are basically long tube-shaped clouds that stretch across the entire sky for miles and miles and miles. They are in the same family of cloud as shelf clouds, and there's a good reason for that. They are actually caused by many of the same mechanisms. Usually they're associated with the gust front of an incoming severe storm. And so that's what this picture depicts right here, is that this roll cloud is coming in front of a storm system. However, something to keep in mind is that they don't have to be associated with severe storms. Sometimes, even in fair weather, there is just horizontal vorticity just in the atmosphere. And if conditions are right where clouds can develop within that vorticity, you can have something like this, which is a roll cloud just in the middle of a clear day. This picture doesn't do a great job of showing it, but this roll cloud stretches across this sky for miles. And in fact, yeah, I do have this picture. This just demonstrates how far these things can go. These things are obviously very rare. The conditions for them to happen do not commonly happen, especially around here. They do happen occasionally over Lake Michigan, though. So if you're ever vacationing over there, or if you live there, maybe look out for these sometimes, because they do happen there occasionally. Next, I wanted to talk about something called hole punch clouds. These are also called fall streak holes, but as the name suggests, they're literally just holes in the clouds. Specifically, they are holes within the cirrus clouds that exist really high up in the atmosphere. If you know anything about cirrus clouds, is that they're composed of a mix of water droplets and ice crystals, just due to how high up in the atmosphere they are. And so how they form is pretty interesting. Basically, whenever an airplane flies through the cirrus cloud layer, what it'll do is there's the wind turbines, or not the wind turbines, but you know the turbines that spin the engines of the plane. They cause low pressure regions around the propellers. What that does is that sparks the creation of ice crystals. And what if you've taken Meteorology 327 with Dr. Choi, you know that ice crystals like to grow and take moisture away from water droplets. And so what happens is that once a plane goes through and creates these ice crystals, it'll start taking moisture away from the clouds. And so it'll just create a ring around where that plane went through of open sky. And so that's what you see on the left here. Usually, though, with fall streak holes, you don't actually see this. What you actually see is something on the right here, where you have the hole, and then in the middle of it, you have the structure right here. This is called virga, and that's basically just snow that is falling and that's not reaching the ground. It's literally snowing up there. Those are the ice crystals that were formed falling out of the sky. And so I think that's a really neat sort of process that's happening there to create these clouds. These are pretty rare as well. Not nearly as rare as roll clouds, though. They can happen anywhere. They can happen here as long as there's just a cirrus deck, and then, of course, a plane that flies through. And the last sort of interesting cloud that I wanted to look at are Kelvin-Helmholtz clouds. This is a type of cloud named after two physicists that really didn't do much for meteorology, but they actually describe fluid flow and specifically fluid turbulence. Um, Basically, what happens is if the conditions are somehow perfect and there's shear within a fluid, so for example, wind shear within the atmosphere, it can create these sort of wave-like oscillations. And if there ever happen to be clouds associated with these oscillations, then you can see these clouds that look like ocean waves breaking on the shore. These things are very rare. Not for the reason you might expect, though. This Kelvin-Helmholtz instability that creates these waves actually probably happens fairly often in the atmosphere. The problem, though, is that you can't really see them because air is invisible, and so the conditions for clouds to form in them, those are the rare conditions, which is why you don't see these clouds. But yeah, I've never seen these before, but I actually have an aunt who took actually, it's neither of these pictures, but she lives in the mountains in Lake Tahoe, and she actually sees these clouds from time to time. The wind shear patterns associated with these waves usually happen after air moves over the mountains, which is why they're more common in the mountains. Um, yeah, I guess that's all I have for you guys. You guys have any questions about any of the things that I've talked about today? Just kind of a short presentation. I didn't want to go too in depth today, so I just kind of wanted to take a time to look at just cool looking weather things, cool causes of weather, that kind of thing. That's all I've got for you guys. Does anyone else have anything they want to comment before we end the meeting? All right. I guess we can go ahead and end the meeting there. Don't forget about t-shirts. We'll have the orders open for at least a few weeks before we order them. So take your time with ordering those. I don't really have anything else to announce. We'll have a presentation next week, probably to do with radar in preparation for the radar conference that's on next Friday. But yeah, that's all. I'll see you guys next week.